All right, let's do an example function composition that we were talking about at the end of lecture A. Talking about these ideas of plugging one function into the other, so to speak, or applying one function right after the other in sequence. What's an example? Well, for example, you could take f of x to be x squared plus 3x plus 2, and you could take g of x to be 2x minus 5. And I could say find f of g of x and find g of f of x, and we'll see that they are different functions. Do it over here. You get me and that in the picture at once here? Good here? I mean, yes. Is this? Okay, they're right here. So f composed g of x is f of g of x. We are plugging the output of g into f, which means that we're doing g first and then f. But as far as formulas go, you can just take the formula for g, this formula that gives you the output of g, and plug it into f, replace g of x with 2x minus 5. And remember, we talked last week about this. No matter what's inside the parentheses, when you look at the formula for the function, replace x by that thing. So looking at that formula for f over there, I have to take 2x minus 5 quantity squared plus 3 times 2x minus 5, and then plus 2. And then the goal would be to simplify this. 2x minus 5 squared, you got to imagine a foil in your head, or else write it out on your own. I get 2x times 2x is 4x squared. The product of the outside and inside from FOIL would both be negative 10x, 2x times negative 5. And I have two of them, so I should get negative 20x. Negative 5 times negative 5 is positive 25. 3 times 2x is 6x. 3 times negative 5 is minus 15. Plus 2. This simplifies to 4x squared minus 14x plus 12 if I've not made a mistake. Feel good? Anybody catch a mistake there? But what if I do it the other way around? G circle f, G compose f of x, plug the output of f into G. Apply f first, then G. What's the formula for f? It's x squared plus 3x plus 2. Yes, take that entire thing, that trinomial, and plug it into the formula for g in place of the x, right there. 2 times the entire expression, x squared plus 3x plus 2, and then minus 5. This does give me a different function, even upon simplification. 2x squared plus 6x plus 4 minus 5. These two things, here and here, are not the same function. This operation is not commutative. There is a special case when it is commutative, and that's when you're composing a function and it's inverse. Given a one-to-one function, f, an inverse function, f inverse can be defined. This notation is unfortunate. This does not mean f to the negative 1 power. If you meant to take a function to the negative 1 power, take the output of the function to the negative 1 power, you would instead write this. Put parentheses around the whole thing to the negative 1, like that. Or write it as 1 over the function, the reciprocal of the function. It's not the same thing. That's the first thing to realize. That notation is a bit unfortunate. But it's kind of what we're stuck with. If we want to be consistent with all the other people in the world. Of course, we could be rebels and do something different, but you want to be able to communicate what you're doing too, right? You got to tell from the context. The domain of F inverse must be chosen appropriately. It equals the range or image of F. So the set of all outputs of F become the inputs for F inverse. I haven't really said what F inverse is yet. We'll see why as we talk about what it is. It is related to function composition. Not giving details on the slide here. Essentially, the equations I'm about to write down are the definition of the inverse. When you compose a function, a one-to-one function, and its inverse, when you plug the inverse into the function, or more precisely, plug its output into the function, you get back the original input. No matter what the original input is, as long as it's in the domain of F inverse. And it works the other way around, because this makes it commutative. Then the composition operation is commutative for a function in its inverse. That's a special case. That also equals x. For all x in the domain of f of x, and technically speaking, you also need to make sure f of x is in the domain of f inverse. So some technicalities there. Technically speaking, the domains of these functions are not necessarily the same. And we'll see some examples of that. But symbolically, this happens. We'll talk about the relationship to the graph of the inverse as we think about examples. So first, let's start with an example of a linear function. Say a function f defined by the formula f of x equals 3x minus 8, a linear function. We call this y for the output. What's the inverse function? We've talked about this before, right? Last week we talked a little bit about it with unit conversions. You want to solve for the independent variable, to switch the roles of what's independent and what's dependent. If I add 8 to both sides, I get this. If I divide both sides by 3, I get this. Oh, y plus 8 over 3. Or 1/3 y plus 8/3. Technically speaking, you are done. That is the inverse function. You could call this f inverse of y. And that would be fine. But wait a minute. My teacher in the past told me now swap x and y. And that's okay to do as well. If we swap the roles of x and y, we'll get y equals f inverse of x equals 1/3 x plus 8/3. There's really only two reasons to do that. They're good reasons in some circumstances. One is just because we're used to having x be the independent variable and y be the dependent variable, and this kind of thing makes us feel it's just not right. That's just a force of habit. More importantly, if you graph the original function and its inverse in the same plane with the same input x-axis, they will be reflections of each other across the 45-degree length of the origin, y equals x. Let's check that here. If I graph f of x in this context, it's going to look about like this. That's y equals f of x equals 3x minus 8. Slope of 3 and a vertical intercept of -8. If you plot this function, it's got a slope of 1/3 and a vertical intercept of 8/3. it's going to look approximately like that. Not drawn perfectly. I was trying to draw this more carefully. I had to use graph paper. And these are supposed to be reflections of each other across this y equals x line. If you take your head, maybe you even want to do it with me here, take your head, turn it a 45-degree angle that way, and you say, hey, mirror image. Some people have a real easy time seeing that. Some people have a hard time seeing that. This part is the reflection of that part, and this part is the reflection of that part. If you can match up points across that line with lines that are perpendicular to y equals x. These points have opposite coordinates. This one, for example, maybe has coordinates x equals, just making something up here, 3, y equals 1 plus 8/3 is 11/3. And if that's the case, then this one's going to have coordinates that are opposite, or that are swapped, 11/3 3. Said this last week. If your variables mean something in real life, if x is time and y, or x is number of widgets to produce and y is cost or revenue or whatever, profit, do not swap the variables when you get the inverse function. Leave it this way. Because otherwise, if you swap the variables, you're messing up the meaning of the variables. So then what do you do about the graphs if you don't swap the variables? Don't graph them in the same picture if you swap the variables. Graph them in two separate pictures. One with axes labeled, watch me here, x, y. The other one over here with axes labeled y, x. It's okay to do it. You can label axes any way you want. Catch that? x, y for the first function, f. For its inverse, y, x. The opposite. Swap the labels. That's better when the variables mean something. How about another example? How about a simple cubic which also happens to be one-to-one? Well, we can't do this for arbitrary cubics, and we actually even can't do it so easily for arbitrary cubics that are even one-to-one. Remember what one-to-one means. It passes the horizontal line test. No horizontal line goes through it more than once. But if your cubic is simple enough, like f of x equals x cubed minus 17 or something, a cubic term plus a constant, then it's doable. Add 17 to both sides, you'll get x cubed equals y plus 17. Then take the cube root of both sides. X is the cube root of y plus 17. You could call that f inverse of y if you like, or you could swap the variables since they don't mean anything. You could say y equals f inverse of x is cube root of x plus 17. Either answer is okay as far as the formula goes. If you want to graph them in the same picture, then use this version. I won't take the time to graph both of these. Maybe you want to on your own after class. That would be a good little thing to do. To see if the reflection property seems okay, that it's working.
Wait, to graph them in the same picture, you do have to swap the variables?
If you graph them in the same picture in the usual way, then you do have to swap the variables. Okay. What's next? How about a linear fractional transformation? Well, that sounds fancy. It's a special kind of rational function. What it is it's a fraction, a ratio of two linear functions. Say that one. Okay? What's the inverse of that? It is possible to solve this for x in terms of y. Think of it as cross-multiplying first. Take, essentially, multiply both sides by 3x plus 4. You can think of y as y over 1 if you like, but you don't have to. Y times 3x plus 4 equals 2x minus 1. We're trying to solve for x. Keep that in mind. We're trying to solve for x. We're trying to solve for x. Distribute the y through here. You get 3xy plus 4y equals 2x minus 1. We're trying to solve for x. We're trying to solve for x. 3xy minus 2x equals negative 4y minus 1. Why did I do that? To get the x's on one side and things that don't involve an x on the other side. And with this one, an x can be factored out. This is x times, in parentheses, 3y minus 2. Now we're almost done. Just divide both sides by 3y minus 2. So x equals f inverse of y equals negative 4y minus 1 over 3y minus 2. Or if you prefer, multiply the top and the bottom by negative 1, you'll get 4y plus 1 over 2 minus 3y. Those are the same thing. And multiply the top and the bottom by the same thing, negative 1. If you prefer, it doesn't really matter which way you write. The reflection property, if I now swap y and x, will work for these functions as well. And that's something that might be worthwhile checking after class. The domain of this function is the range of this function. The domain of this one is everything except where you'd be dividing by 0, everything except 2/3. The range of this one is everything except 2/3. I'm not going to verify that here, though a big hint is provided by the ratio there, 2 divided by 3. That's a big hint that 2/3 is correct, though I'm not going to explain that. Okay, but it's doable. A little tricky, but doable. Logarithms are also an example. We'll save that for Wednesday. Many functions are not invertible, however. They're not one-to-one. They fail the horizontal line test. There are horizontal lines that go through the graph more than once, like graphs that are parabolas fail the horizontal line test. There are many horizontal lines that go through it more than once. They're not one-to-one. They're not invertible. Functions which are not one-to-one are not invertible. However, we might be able to fix things. We might be able to restrict the domain, make the domain of the original function smaller, so that the function does end up passing the horizontal line test, and it is one-to-one. How do you restrict the domain? The answer is it depends. It depends on what the situation is. Depends on what the original function is. We're going to talk about how to do it for quadratics here in a few minutes. So that's the main topic we're moving into now, is quadratic functions. I'm going to go through this pretty fast because we're running low on time. So if you're writing notes, you may want to just paraphrase things or look up on the Google Drive folder later today. I'll try to put this in there by 2 o'clock today. First of all, why are quadratic functions important? Maybe you don't want to write this down. Just listen. I'm going to go through this quick. They're important in physics. There's lots of physics applications where they come up. Free fall, for example, which if we have time, we'll look at a quick free fall example today, where an object is dropped, or you throw it straight up and it comes back down. Or projectile motion, where you're shooting the object somewhat sideways as well, like a baseball player hitting a ball. With the straight up and down motion, a quadratic function still is relevant. It's a function that gives you the height in terms of the time elapsed. With projectile motion, Height is still a quadratic function of time, but it's also a quadratic function of the horizontal distance traveled, as well as time. Both things. In finance, we'll look at examples where the yield rate, the rate of return for an investment, can sometimes be found by solving a quadratic equation. It's a pretty limited set of circumstances that happen, but it's worthwhile to talk about anyway. Rate of return for investment is just, what kind of return are you getting? 20% rate of return would be better than 10%, for example, better than 5%. And differential equations, this class that we have at Bethel and other schools where calculus is used a lot. Quadratic functions can come up, for example, in determining when a population model experiences a big change. And I'm being purposely very vague, all what I mean. We will get into details later in the semester. What are quadratic functions? Here's their standard formula. F of x equals ax squared plus bx plus c. Right, you've seen that before? Starts making you think of the quadratic formula, or it should at least. What do those constants a, b, and c represent? C is the y-intercept, or initial value of f. Because when you plug in x equals 0, you get c. The constant b is the slope of the graph at x equals 0. So if b is positive, then the graph of the quadratic passes through the y-axis with a positive slope, though it's not a straight line. It's in general going to be a parabola. But this would be where b, the slope is positive, slope equals b is positive. Here's another situation where it's positive. One graph looks like this. Slope equals b is also positive there. A tells you about the concavity. When A is positive, the graph is concave up. It looks like a smile. This is A positive. When A is negative, the graph looks like a frown. It's concave down. Does that mean concave down graphs are bad and concave up graphs are good? No, they are neutral. Neither good nor bad. It just depends on the situation. Which one is applicable? The graph is always a parabola when A is non-zero, like one of these. Is everything that looks like that a parabola? The answer is no. Technically, the definition of a parabola is very special. It's a special kind of conic section. I'm not going to get into the details here about what that means. But if you're interested, you can do research about parabolas. And parabolas are important, actually. They're important in real life, not just for physics free fall, but also, for example, for constructing telescopes. The kind of telescope, I forget what they call it, where the light comes in, bounces off a mirror, and reaches a focal point after it bounces off the mirror. Parabolas are important for that. The roots of f, or zeros of f, are given by the quadratic formula in all its glory right there. Make sure you only use this when solving an equation like this where the right-hand side is 0. If it's not 0 over there, you got to subtract it from both sides to make it 0 before using this. How do you memorize the quadratic formula? There's a song. Dare I sing it? I dare. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. There we go. You can clap. Come on, there you go. Okay. It was okay. Right? Pop goes the weasel song. Make sure zero's on one side before you use it. The thing under the square root has a name. It's called the discriminant, b squared minus 4ac. And when it's positive, then you have two real number roots. You've got two x-intercepts. If b squared minus 4ac is equal to 0, then you actually only have one x-intercept. The graph would just touch the x-axis at one point when b squared minus 4ac equals 0. And if it's negative, then, oh boy, imaginary numbers come into play. Do imaginary numbers have real-life applications? They actually do. The general subject is called complex arithmetic, or complex numbers, or complex analysis, which sounds like it's a bad thing because it's making things more complex. Actually, the great irony of complex numbers and complex analysis is it makes problems simpler in many situations. Imaginary numbers and complex numbers can make some problems, not all problems, but some problems simpler. That's the amazing irony of the name. And so they're worth learning about. If you take differential equations, you'll learn about some applications of complex numbers. All right, about to go on to the next slide, continuing to go kind of fast. More on quadratic equations. Oh yeah, we got to go really fast. Using the method of completing the square, every quadratic function can be written in something called vertex form. A times in parentheses x minus h quantity squared plus k. If A is positive, then the graph is concave up, and the graph has a minimum value. That minimum value point is called the vertex. Its coordinates are h comma k. K is the actual minimum value of the function in that case. H is the value of x where it occurs. If A is negative, then the vertex is at the top of the parabola. We still label its coordinates hk. But now k would be the maximum value of the function. H would still be the value of x where it occurs. Maximum and minimum values of functions is really important in calculus. That's the main application of calculus. With quadratic functions, you don't actually have to use calculus to find those points, but with other functions, you do. Okay? Hang with me here, we're still got another slide to go over. This vertex form can be found by completing the square. I think what I'll do is I'll give you a maybe a Khan Academy video or something where they show you how to complete the square. Right? It's a tricky method to write it this way. Find maxes and mins. It also can be thought of in terms of transformations. Horizontal shifts, vertical shifts, horizontal compressions or stretches, vertical compressions or stretches, maybe reflection across the horizontal axis. That's in the reading. Maybe I'll find a video or two on that as well. One more slide. Quadratic functions are not one-to-one over their entire domains. They fail the horizontal line test, right? There are horizontal lines that go into them more than once. If we restrict the domain property, we can make them one-to-one. Like just use half of a parabola, like either this or this. Those pieces of the graph do pass the horizontal line test if you're only focused on those pieces and nothing else. Vertex form is the most convenient way to do that, to define the domain so it's one-to-one. Be careful what the inverse function is. I think after class today, I will then solve this problem and send you my solution to help you understand this process with an application. Okay? Technically, I have 1 or 2 minutes left, maybe? Yeah, 2 minutes to find your group numbers for this week for the next grade of 1%.